All right. Lynn gave a great introduction, and you all know why you're here. This is Rap Bradley lecture series, and we are here to listen to Professor Peter Hall. This is the only time I'm going to call him Professor Peter Hall because he does not like to be called Professor Peter Hall. And Peter will give a talk, the after dinner talk. And this is the, as all of you know, this is the 21st Bradley lecture. And you've also heard something from Lynn about Bradley. I was very fortunate to be a very young faculty member. Came here in 1987, and Bradley was a faculty at that time. And of course, I used to have lunch with him in the afternoons, and his head would always be down because he would be doing crossword puzzle all the time. And once in a while, he'd lift up to say something while I'm having my lunch. And of course, I interacted with him. And then I figured out that, okay, if this guy is good at crossword puzzle, then, I need a proofreader for my papers. So I should give him my articles. He would religiously proofread everything, and he would point out things and pick out the grammatical errors and so on and so forth. He did a great job, and he was a great colleague, and we all dearly miss him. And of course, if you want to really hear about everything that Ralph Bradley did, up there has posted a video of John Stufkin go over his entire life history on YouTube. So you should probably click on that. I don't want to have a take two of that. Instead, I'll just focus on some of the things that Ralph did. Of course, as Lynn mentioned, for 20 years or so, he was the head of Florida State, and he really grew the department to a very well-known department in the country. And then he came here in 1982 and had a very productive career until 1992. And he also hung around after that, and of course he passed away in 2001. Today we are here to listen to Professor Peter Hall. That's the second time I've said that, I guess. Okay. I had a wonderful chat with him this morning, and he told me about some of the things. I essentially asked him, how did you get started with all this? Of course, he was always interested in mathematics, and he was solving problems from fellow Volume 1 and Volume 2 and so on and so forth. He got really interested in probability theory, and he wanted to work in probability theory. And then he joined the master's program in Australian National University. And pretty soon he said, okay, instead of taking the courses and so on, I'll just start doing research. And he got his master's by doing research. Chris Heide was apparently his major professor at that time. And Chris said, well, you can't just hand in your thesis now, and there were some technical issues and so on and so forth. So he actually got his master's degree in 1976 in Australian National University. At the same time, he got his DPhil in Oxford. And of course, in Oxford too, he worked under John Kingman, Kingman and Taylor, I guess, yeah, and worked independently and produced a thesis. And apparently, he photocopied everything that he wrote and mailed it to him on a Friday, and Monday morning Kingman had signed off the thesis and said, good enough, you're ready to graduate now. So essentially, everything learned essentially by himself, and got interested in probability theory, and did a lot of work. And in 1980, I guess, he wrote a nice textbook on martingale limit theory and in its application with Chris Heide. And if you look in my thesis, it's about 85 pages or so. After a while, I started calling it HH because I was referring to Hall and Heide so much. My advisor said, just abbreviate it as HH 1980, and that's what you're going to do from now on. And I cashed in on that book, because anytime I got stuck in any of the mathematical arguments, you go turn a random page, you'll find some argument, and then I'll start using it. And of course, if I refer to Hall and Heidi, the referee is not going to ask me any questions. He'll say, okay, that must be correct. Okay. So, and carried on, and of course in 1988 or 89, he got the COPS Award, and from there on, he got numerous awards. He's written numerous articles, and Steve Madden, by the way, in Chapel Hill, told me a nice story when I had lunch with him when I was on a sabbatical in 1992. He said apparently they were working through the day, they were trying to prove something, and they were stuck, and in the evening, Peter said, well, you know, I need to go home now because I have to leave tomorrow. And Steve said, okay, we'll try this proof some other time. But Peter said, no, I'll try give it another shot at the proof tonight before I go to sleep. And hopefully I can leave the proof in your mailbox before I leave tomorrow morning. Lo and behold, the proof was there in this mailbox the next morning. So he's just done fantastic amount of work in so many different fields, and can't begin to list any of those. And I just looked up his webpage, and he has, since 2001, 189 articles. Okay, and 39 in the Annals of Statistics, 28 in JRSSB, 18 in Biometrica, 16 in JASA. 1 in the Annals of Probability. Remember, he started out in probability, and he is slacking now. Sorry about that. And I looked at yearly records and so on. Boy, tremendous. I wouldn't want to be head of the department where he's a faculty member, because I can't tell him, no, you need to write a few more papers to get this or get that. But that's Dr. Hall, and he's still going strong, and the list just simply goes on and on. We heard a nice talk during this afternoon, and we will hear another talk on excitement of statistical science today. Peter.
I have to stay away from that speaker.
Yes.
Doesn't like me. Thank you very much for that unduly generous and there's remarks that took a bit of poetic license there. Thank you. Thanks very much. I want to talk to you a little about the excitement that I feel in statistical science today. And obviously, because it's the excitement that I feel, I'm afraid I'm going to talk about some of my own work as well as more important work of other people. I think I've prepared this talk a little while ago, and then I decided to add some material, and I think if I've got it timed right, I'll be able to stop just before I get to the technical part, which is probably what you want for an after dinner talk. I could start with let H be a Hilbert space, but you're probably not looking for that. I want to talk initially about a lot of the advances that those of us who are as old as I am have seen, particularly in computing technology. I was talking to one of you this afternoon about something that I've noticed. Today, if you want to submit a paper for publication, they usually won't even look at it unless the method that you're suggesting is capable of being done, being applied to moderate data sets in a small amount of time. Whereas if you go back and you look at the history of particularly non-parametric statistics, you will find that 80 years ago, people were working on topics like permutation testing, which really didn't become feasible from a practical point of view for another 40 years. It was really only in the late 60s or about the mid-70s, during that period, it became really practically feasible to use a permutation test because the capacity of electronic computing devices had got to a stage where you could do the simulation required for permutation testing, but that didn't pardon me, stop a whole range of people from working on permutation testing from the 1930s right through to the 1970s. So I think it's kind of ironic that today the capacity, our access to computing power has tended to dictate our ambitions in research and statistics. And of course, this is one of the availability of computing power was one of the things that gave Efron's bootstrap idea wings. These resampling ideas had been used before. In terms of how I see the development of the subject, it actually has its heart in India, its root in India. A mixture of the work of the extraordinary Indian statistician Mahalanobis and a person who's obscure to us, but not to some of our colleagues in Britain, an Indian civil servant by the name of John Hubbock, who had to estimate the variance of crop yields in Orissa in India. But Efron took this idea and he showed how it could be applied much more generally than Hubbock or Mahalanobis, or Mahalanobis, sorry, I always get that, yes. The development of interactive computing, where you didn't have to walk a few blocks and put your punch cards in a machine and come back the next morning and look at the printout and then find that you had a bug in your code and you had to do the whole thing again. In Australia, that really only became possible in the early 80s, where you could do it from a console down the corridor. I think it was similar in many places in the US. And of course, this explosion in computing power is something that we refer to today as Moore's law, which argues that the number of transistors that we can fit onto a microprocessor effectively doubles about every 18 months. This transparency, which is stolen from Wikipedia, shows actually how close it is to a straight line fitting a model where the growth is the growth is a doubling every 18 months. The vertical axis is the logarithm of the count of the number of transistors on a microprocessor. But what we probably don't appreciate quite as keenly, because we don't observe it happening right under our nose, is the fact that new developments in technology affect not just the computing devices that we can use to analyze data, they also affect greatly, first of all, the type of data that we can gather. We can now gather data automatically. We don't have to have people present to record it, and that means we can do it in enormous quantities day in and day out, night in and night out. But they also affect dramatically the sorts of questions that we ask. We are able to look at because we can gather data on things we never could before, for example, on what happens not just at genes, but at many other points on the human genome. We can ask questions about what's going on in these places that we were never able to before. So advances in technology have changed not just the way we can process the data, the sort of methodology we can use, but they've changed, first of all, the nature of that data, and much more fundamentally, the sorts of questions that we ask. Some of the sorts of data, perhaps I should have, can we go back? I know it's all right. Yeah, just the bottom of this transparency here, I omitted to mention specifically new data types in genomics, where we now have very large data vectors from samples that are really very small in comparison to the length of the data vectors perhaps in the tens of thousands if we're looking at genes themselves, in the hundreds of thousands, 500,000 if I can recall correctly some of the work of some of my colleagues in Melbourne. on SNP data and data at other points on the genome. Another example of the way in which type of data we're looking at has changed is the much greater access to functional data, again through recording everything by machine. Arguably the first work on functional data analysis was by C.R. Rao in India in the 1950s, but all the data he analyzed were recorded, of course, not by machine, but by human beings. But today, particularly with spectrometry, with data in spectrometry, we are, as in the context of the human genome, looking at perhaps tens of thousands of measurements at the same number of wavelengths or frequencies. And I want to mention particularly an example in chemometrics, in food science. This is a data set of infrared spectra of 100 wheat samples. This isn't data that I worked on, it's data I've worked on myself, but not that I gathered myself. But I worked with a colleague in Canberra. He was funded by a conglomerate associated with funded by bread manufacturers in Australia. And the idea that he and I were working on together was to be able to determine from a sample of wheat that you may have got in from a storage pen in a farmer's, on a wheat farm somewhere, what the bread would taste like if you were to make the bread from that wheat. And this, according to what my colleague had discovered, this really depended on the relative proportions of 3 different proteins in the wheat. Now, of course, one way to do this would be to take the sample of wheat and send it off to a laboratory, and within a couple of weeks you'd get the results back. But by then the farmer would have sold the wheat to somebody else. So you needed to be able to determine the levels of protein on the spot, on the farm. You can get access to very reliable data on the infrared spectra, that is the brightness, the amount of light that's reflected in a section of the infrared spectrum using a handheld spectrometer. Used to be, it was thousands of frequencies or wavelengths that this was measured at. Now it's tens of thousands, and you can build a classifier based on these data for measuring the amount of the amount of protein in the wheat. And this data set I'm talking, it's a benchmark data set used in the chemometrics community, and now also in people working in functional data analysis. And one of its interests is it has a relatively small number of samples, data points in each training sample. We're looking at trying to classify wheat on the basis of whether it has a low number or a low level or a high level of protein, of units of protein according to these measurements. And this, wait a minute, where have I got here? This spectrum here shows, so these figures here show the spectra from these 2 data sets. What I think there's 41 in the first data set and 59 in the second, so the total number of points of curves in the training data is 100. These are data sets that are recorded from a small portable spectrometer like the ones I described. The idea is to build a classifier that would determine whether the protein in a new sample with a spectrum that you've just gathered from the farm has a low level of protein or a high level of protein. Here we're looking only at 1 protein. In the classifier I was working on with a colleague, we were looking at 3. And you can see that these 2 populations are really quite similar in terms of the shapes of the curves, where the peaks in the spectra are. You can probably see some differences between the 2, the low protein Samples have the highest peak a little bit higher than the highest peak in the high protein samples. It looks as though you would be hard pressed to construct an accurate classifier using these two data sets, given how close the spectra are. That's what I thought when I first looked at the data and worked on the problem. But actually that turns out to not to be the case. By making use of high dimensional characteristics of these wheat samples and determining those characteristics so as to optimize the performance of a classifier, you can build a classifier whose error rate is something like 2%, the overall error rate for a new sample of wheat. And this is an example of the sorts of power you can get by exploiting the high-dimensional nature of a great deal of modern data. To get something like that error rate in a conventional statistical problem, you would really need one of the variances of the population to be much smaller than the variance of the other, so that the data in one population were much more highly concentrated around a point than the data in the other population, or something like that. But we can see from the spectra that nothing like that is going on here. The key to getting good classification performance here is to look towards the relatively high frequencies, determine which of those high frequencies are responsible for most of the differences between the spectra, and then to focus all of your attention on those particular frequencies. Now, this is in the context of functional data analysis, where sparsity is not the main issue. But of course, that's quite different in high-dimensional data analysis for genomic data. We know that we're looking at perhaps 24,000 genes on the human genome, if we're just confining attention to genes. The suspicion historically has been that only a handful of those genes, perhaps somewhere between 5 and 15 of those genes, would be particularly influential in causing disease. And the challenge is to determine those influential genes. And this problem is answered in much the same way, in a sense, as the problem about determining whether a new sample of wheat has less than 15 or more than 15 units of protein in it. It's answered by building a classifier to discriminate between the two populations. But we have to remember here that our aim is not to classify a new person who wanders into the doctor's studio as having some sort of acute leukemia versus not having it. The reason we're building a classifier is not to make a classification decision, but to determine which of the genes in this case have the greatest impact on the success of the classifier. So now we're using a classifier not really for the purpose of classification, but for the purpose of variable identification. And that's really one of the ways in which our analysis of this type of high-dimensional data has changed. We build a classifier not at all because we're interested in classification, but because we're interested in variable selection. And of course, because the number of influential bits of the genome here is really very small compared to the number of bits we're focusing attention on, there's the issue of sparsity, of having only a small number of needles in this haystack to find. We discussed at lunchtime today a discussion which is going on in some areas of the genetic community about whether we should be doing that. There is some suspicion by some leading geneticists, particularly in the US, that our mathematical models have been a little too simplistic, that probably there's more than half a dozen, more than a handful of genes that have a significant impact on whether a person's going to develop one sort of disease or another. And we're seeing increasing evidence as we develop new ways of making measurements of what we have on our chromosome. This is true. For example, many of you will have read articles about gene switches which indicate that it doesn't really, it's not all down to whether you have a mutation or not, but whether that mutation is in some way pressed into active service. And as we look further at many more aspects of the genome, we're finding that there's a much greater number of transcription errors in going from parents to children. There's a lot more misreporting of genetic data in terms of what our genes are doing, and the problem has become ever so much more complex than it used to be a little while ago. So the issue of how we determine what we mean by sparsity is something which is continually evolving. Now, I want to conclude by looking at a problem that, again, I talked about with a young colleague here this afternoon, which really captivated me when I first heard about it, and it's the work of David Donohoe and Jason Jin, published in an article in the Annals of Statistics, 2004, but actually has a much longer genesis than that. Goes back at least to work of Tukey in the early 1970s, and it's to do with our capacity to detect signals, very weak signals, without being able to read them. This came to me as quite a shock when I first heard about this work. It was an exciting shock because it opened up possibilities that I'd never even thought about before. I think those of us who've done a little bit of work in time series have always felt that if we're looking for a signal, we should try to find some evidence of its size, really. We try to estimate the signal, to be frank. But this problem, which, as I said, goes back to Tukey, although he didn't, I think, appreciate at all the theoretical dimensions of it that were elucidated by Donohoe and Jin, and before then by Yuri Inkster in Russia. This problem shows that it's quite possible in theory, and as I'll mention in a minute, also in practice, hopefully, to detect the presence of a signal without being able to read it. Tukey's idea was that you would test, you imagine a signal comes in lots of discrete bits. Tukey's idea was that you would test each bit for the presence of a signal, and you would then look at the statistical significance of the number of significant hypothesis tests that you got in this process. That was how he conducted his statistic, which was dubbed the higher criticism statistic by Donohoe and Jin. Earlier work by Yuri Inkster had produced a much more complex method that was capable of producing a result with the same theoretical power, the same capacity to optimally detect a signal when it was possible to detect it, even if it wasn't readable. The signal was so weak that it wasn't readable. This method is now being used by a number of people, including some of my colleagues at the University of Melbourne in the Department of Physics, to try to detect what are known as gravity waves. And this brings me back, in a sense, to the theme of my talk earlier today on astronomy. The study or the search for gravity waves is, I think, in this country as well as my own, generally regarded as a playground for astronomers, but it requires a great deal of ingenuity and ideas drawn from a number of areas of the physical sciences, including both physics and engineering. Anyway, if you use these ideas of Donohoe and Jin, Donohoe and Jin essentially showed that the method of Tukey that Donohoe, I think, heard about in an undergraduate lecture at Princeton in the 70s, is mathematically optimal. But the idea for the statistic goes back to Tukey. And this idea of looking at the statistical significance of the number of significant hypothesis tests for the presence of a very weak signal actually turns out to have substantial advantages over competing methods for detecting gravity waves. And there's a certain range, a certain type of waves known as phase wandering sources, where it has a 30% improvement over any other method that has been tried. This is obtained, of course, from numerical simulation, because, as I'm about to point out, really nobody has ever seen a gravity wave, although we have seen evidence of them. Now, as you're probably aware, Einstein's theory of relativity, general relativity, going back to 1916, indicates that gravity affects the shape of space and time, and that paths of light change their shape from being completely straight to being slightly curved under the influence of gravity. And as a result, if there's a big explosion somewhere in the galaxy with lots of mass suddenly changing its position, then there will be a sort of a ripple in the forces due to gravity spread through the universe. This sort of explosion might result from the explosion of a supernova, for example. The gravitational distortion spreads out in ripples, like you put a rock into a pond. The only catch is that these ripples are much less visible than ripples in a pond. As I said, we haven't detected such waves. They're hypothesized by Einstein's theory of relativity, but their evidence has been felt in terms of sort of second-order effects. The theory of relativity allows us to calculate the effects that the gravitational radiation would have, so that these waves would have if they were to exist. And going back to 1974, the American physicist Joseph Taylor and the PhD student Russell Hauser detected these second-order effects. They didn't detect the waves themselves, but they detected what are believed to be the influence of these waves. And as we know, the Nobel Prize Committee works rather slowly. Some 19 years later, they were awarded a Nobel Prize for their efforts. Oh, and this was a picture. I was never able to get this picture into my set of transparencies in such a way that I could be sure that it would come out horizontal. So in the end, I stuck with it. But this is a NASA picture of gravitational waves. Not actual gravitational waves, stylized gravitational waves, flowing away from an explosion of a supernova in the middle there. As I said, the actual waves have never been detected, and there's an effort on now to detect them. And it's in conjunction with that effort that people are using the ideas that Donohoe and Jin put forward to all of us in the annals of statistics in 2004. A major part of the problem, of course, is that gravity is very weak, and moreover, the bodies in the universe that are probably going to be responsible for generating the waves that we observe are very large in size. So that this results in the wavelengths of these gravitational waves, assuming they do exist, being very long. And so detecting something which is very low amplitude and very long wavelength, changes in the gravity of that type is particularly challenging. The way in which physicists often attempt to solve these problems, they kind of know what they're looking for, but they try to magnify it so that it becomes measurable or detectable at least. As we're looking at the ideas of high criticism, we're looking for something which we can detect but probably can't measure. So we're looking to detect it. So they try to magnify it. And to do this, they use the principle of interferometry. Interferometry is used widely in astronomy. I'm familiar with its use in radio astronomy, where this is an interesting story. In the early 1940s, Australia was concerned that it would be invaded by the Japanese. And we built a radar detector on the coastline in Sydney, looking out to the Pacific, because we expected that's the way the Japanese would come from. And so it was fixed, it didn't rotate. It was just fixed, pointing due east. And every time the sun rose, and that's where the sun comes from, out of the east, we noticed a substantial increase in the amount of radiation in radio wavelengths. And this was really the first discovery of that the sun emitted a lot of radiation that gave us a lot of insight into what was happening in the sun in radio rather than visible wavelengths. And we used the surface of the sea, the surface of the Pacific Ocean, to help us construct an interferometer. That is, we looked at the waves that were received directly from the sun when it rose over the Pacific, and we then combined those with the waves that would hit the surface of the sea and then were reflected up to the radar receiver. And the combination of these two waves arriving out of phase helps to magnify the signal that you're receiving. If you do it in just the right way, and if you know how far below you the sea is and what the angles that things are coming at. And that's the same principle that the LIGO people, the people who are interested in developing laser interferometer gravitational wave observatories around the world, are using to try to magnify the effects of gravitational waves. They're not magnifying the waves themselves, but these gravitational waves would move atoms by an amount that was less than the width of the atomic nucleus. But if you magnified that appropriately, if you magnified it enough, you would be able to detect them. And these observatories are built in the form of L-shaped detectors, arms that are 4 kilometers, 3 miles long, and these two arms allow for the interfering waves in the same way that the sea did off the coast of Sydney in the early 1940s. And that is the manner in which we hope to be able to, with the help of work like that of Donohoe and Jin, we hope to be able to observe the presence of gravitational waves. Now, these detectors are so sensitive that they're influenced by all sorts of other effects too. For example, there are gravitational waves detectors in Washington and Louisiana states here in the US, and also in the UK, Italy, and I think one is being built in China. I'm not sure whether the UK one is in operation yet, but I think the one in Italy is, and the one in China isn't yet. The one in Washington state is well inland. It's a bit over 200 miles from the Pacific Ocean, but I'm told that it's so sensitive that it can detect the waves breaking on the shore of the Pacific. It can detect changes in the it can take gravitational changes due to waves coming in from the Pacific. So you can imagine it could detect a bus going past on a highway or something like that. And this is the sort of a problem that creates the noise that the higher criticism method of Tukey, as developed further by Donahoe and Jin, was trying to avoid. So in order to try to remove that sort of effect, all these stations are supposed to be in operation and to gather simultaneously information about the effects of gravitational waves as they pass through the Earth. And this is the reason for having so many of them. We're trying to get funding for one of them in Australia, but I don't think our government's going to be very, very kind to us there. I think we're going to be relying on the US and other countries for participation. One of the things you'll appreciate is that we have to be able to detect the presence of we have to be able to measure phenomena at really exactly the same point of time in each of Washington and Louisiana states, and also the UK, Italy and China. We have to be able to measure time extremely accurately. And I know that's one of the technologies that one of my colleagues in Australia was working on for a long time. It involved keeping a bar of metal extremely cold and measuring its vibrations at a temperature very close to absolute zero in order to try to measure time with the sort of accuracy that's required. So this is an operation which, as you can see, it's of Nobel Prize winning significance. It involves physicists and engineers from all around the world, and critically it involves statistical work, and in particular it brings together the contributions of some of the strongest statistical scientists in the US, for example Tukey, Donahoe and Jason Jin. Thank you very much. And if you have any questions, I'll try to answer them, but don't ask too much about the physics.